We will continue our quantum statistical mechanics topic, and in this lecture we will try to develop calculations for a general case. But our question will remain the same, which is that if we have a large ensemble of particles n and they are all in thermal equilibrium, so what will be the probability that we randomly select some particles which will possess a specific energy EI? We know that at absolute zero, all the particles are in the ground state. And as we rise the temperature, the higher level starts getting populated. So if we reach a thermal equilibrium and we pick a certain set of particles, then what is the probability that we will select, that we would have selected those particles with a certain energy? And we will now start with a general case. So the general case is the general case. The general case is that if, for example, in the previous case we selected the infinite square well, and now we are having any arbitrary potential. So potential is any arbitrary potential, and we are having the energies of particles is E1, E2, E3, and so on. And we will now consider the degeneracies as well, like E1 energy. E1 is the energy which is possessed by some particles in this ensemble. This is D1, and the degeneracy of the E2 is D2, D3, and so on. Now, let me discuss degeneracy. We know that when two or more than two states, different states, distinct states, possess the same energy, we call those states as degenerate states. So here we can take an example. For example, the hydrogen first level is E1, which is minus 13.6 electron volt, and it is the only orbit that is having this energy. So I say that D1 is 1. But if I consider E2, means the second level, then this is divided by 4, so this is minus 3.4 electron volt. Now consider that for n equals 2, we are having L equal n minus 1, so this is 1. When n is 1, then m is from minus 1, 0 to 1. So we are having three different states, and these three different states, distinct states, this is the orbital, and this is the addition to that, the m. We have already discussed this thing. So we are having three distinct states, and they have the same energy. Means the energy depends only on n, so they have the same energy, and in this situation we are having our D2 equals 4. So even if we don't count spin, not counting spin, so even if we don't count spin, our 4 levels means 1 and 3 here, so we have the degeneracy equals 4 here. energy only depends on n. Now we start with our derivation of the general case. So let's consider that we are having same mass particles and the mass of them of each particle is m, and the total number of particles is n. So we will consider a configuration, and configuration will be n1, n2, n3, and this will be a given configuration such that here we know that n1 is the n1 particles. It means we are having n1 particles with energy E1. Then we are in one, maybe one particle, maybe 2, 3, or any number of particles. While if they will have the energy E1, similarly in two particles are having the energy E2, E3, E3, and each of the level is having these is the degeneracies. So we will now ask a question, and the question is that the question here is in how many ways. So that way I denote by Q, and I write N1, N2, N3. In how many ways are Q? Can we build such a configuration? Can we build such a configuration that is how many distinct states, that is how many distinct states correspond to this configuration, correspond to this configuration. So this is our question. If we are having an ensemble of n particles such that in which we are having n1 with energy E1, n2 with energy E2, now this configuration will depend on the nature of particles. Like if we will have distinguishable particles, the result will be different, or we have identical fermions or identical bosons, then the calculation will be different. So to address this question, that in how many ways we can find a given configuration. Like in the previous example, you remember that we were having a configuration, we were having 5, 7, 70, and the number of ways we can build a configuration in that one was 6 ways that we can build a given configuration from this one. So here Q was equal to 6. So the number of ways in which we can arrange these particles is a configuration. Now this gives us reason why we are interested in finding the number of ways, because this gives us the most probable configuration, and we are behind that one, that we will have to find the most probable configuration, and that will in turn will have maximum probability, and that we want to find here, that we want to find such a way that will be the most probable way, or which will have the maximum probability for a certain energy or specific energy. So the very we know that the number of configurations, it depends on the nature of particles as well. If we will have distinguishable particles, the calculations will be different. While for the identical fermions and identical bosons, the calculations were different. So we will discuss each case individually, and let's say I start with case 1, and case 1 is the case of distinguishable particles. So in distinguishable particles, we are building N1, N2, N3 from N particles. So let's start with this. Let's say first we want to pick N1 particles from total number of particles N. So in how many ways we can do this thing? Let's say I consider an example. An example is, in how many ways can we pick 2 particles? Let's consider an example of 5 particles. So in how many ways can we pick 2 particles from 5 particles? So let's say we are having like 5 particles, 1, 2, 3, 4, and 5 particles. So if the total number of particles are equal to 5, and out of the n is equal to 5, I want to pick N1 particles, and here N1 I am saying that I am picking 2 particles out of 5. Now how many ways I can do this? So the very first one, if I pick first particle, then how many choices I do have? If I pick 1 particle, I can pick 1, I can pick 2, I can pick 3, 4, and 5. So the number of choices are 5. So I have 5 choices. Either I can pick 1 or 2 or 3, 4 or 5. And now when I will pick the second particle with this, pick second particle, then how many chances or choices do I have? I will have n minus 1 choices. And n minus 1 choices will be, means I can pick 1 and 2, I can pick 1 and 3, I can pick 1 and 4, 1 and 5. So I have 4 choices. Or I can pick 2 with 1, then 2 with 3, 2 with 4, 2 with 5. So I will have n minus 1 choices, and here n minus 1 choices means that I have 4 choices. I can pick, for example, 5 with 1, 5 with 2, 3, 4. So in all the cases, I will have 4 choices, mean 1 less than this one. So I can write this one, that how many choices I do have, like I pick 1 with 2, 1 with 3, 1 with 4, and 1 with 5. I have that with 2 I pick 1, with 2 I pick 3, and with 2 I pick 4, and with 2 I pick 5. Similarly, with 3 I can pick 1, 2, 4, and 5. And with 4 I can pick 1, 2, 3, and 5. And with 5 I can pick 1, 2, 3, and 4. So how many choices I have? 1, 2, 3, 4, 5. 5, 1, 2, 3, 4. So 5 into 4 choices. So the total of choices are actually 20. 5 means n and 4 means n minus 1. So I have n into n minus 1 choices of picking 2 particles from 5 particles. But we know that if I have, means now generally I talk not in terms of 5 and not as 4, but if I have n particles, then the n particles, the number of choices will be, as it is n, the next will be n minus 1, and then it will be n minus 2. If I want to pick 3 particles, for example, from this 5 particle case, then the number of choices will reduce by this one. Like earlier, for the first particle, choices were 5. For this, picking the second particle with it, choices were 4. And now if I pick 3 particles, then choices will be 3. And if I pick 4 particles, choices will be n minus 3. So choices will be 2. And if I pick 4 particles, choices will be n minus 3, so 2 choices, and 5 particles I pick, so I have 1 chance. I pick all the particles. And this way it will continue, and it will reach, like this will continue, and it will reach, like generally I can write n minus n1 plus 1 choices. Like the last one will be 1. So that is means multiplied, something multiplied by 1 will give the same thing. So look here, that if I want to now write this thing in terms of the number of particles that I am picking. So what will be the total number of choices? So look here, I can check, means n1 are the number of particles I am picking from n particles. So check this one, that when n is equal to 5, when n is equal to 5, and I'm picking in 1 particle, which 2 in our case, so what will be this one? 5 minus 2 plus 1, and we are having 4 choices. We got this one bit to pick the second particle with it. The number of choices will be 4. So find 5 minus 2, 3, and plus 1, 4. If I now consider this one, the first case, then here, for the first case, what is it? This is n equals 5 and n1 is equal to 1. Then I am picking one particle here, means pick the first particle. So what will be the situation? 5 minus 1, and this is 4, plus 1, so 5. So I have 5 choices. When I pick the second particle, then the number of choices are 4. If I am given the situation that n is equal to 5, but n1 is equal to 3, I am picking 3 particles. Then 5 minus 3 plus 1 and 2 plus 1, 3. So these will reduce. If I want to pick n1 is 4 particles, then 5 minus 4 plus 1, and this is 2. If I want to pick n1 is 5 particles, then it means that 5 minus 5 plus 1 is equal to 1. So what does it mean? Increasing the number of picking particles will reduce the number of choices. So this way I have, this is the number of choices I can pick certain number of particles.